So what we're doing is we've got petri dishes with milk in it, and in the milk we put 4 different colors: red, yellow, blue, and green, opposite each other, so we're in 4 different corners of it.
Yeah,
Okay, we're going to be.
Mine's kind of lit.
Oops.
Like it's not corners anymore.
Would you like to start again? Or?
Will it still work if we don't?
Yeah, grab a new one, and I'll give you some more.
Look.
Yeah, the green is pretty
Will the table fit and then the whole?
It looks like
Okay, we're going to be talking about different kinds of forces today after we do some more gas laws. And so this is part of what we're going to be talking about: polar, non-polar, hydrophobic, hydrophilic. What I've got on the toothpick. So you sort of see that the milk is sort of keeping the food coloring away from each other.
Not really.
Okay? Wherever you put the food coloring, it just basically stays. It doesn't move around unless you're jiggling. Okay? If you jiggle it, then it will mix colors. Okay. What happens here is we've got fat globules in the milk. On the toothpick, I've put some dish soap. The dish soap will break down the fat. So I want you to stand it in between all of them in the center and see what happens.
What?
Oh, goodness.
Oh, I like it. Just made yellow. It just made yellow.
Keep it in there.
Now we got it.
Now, if you want to, you can play with it in different places and see what happens. The fat is being broken down by the dish soap, and so it's starting to move things around. That's what soap's supposed to do, is break down fats and help you clean dishes, right?
Tell me I can drink
Okay.
soap.
Huh?
You can tell me I drink soap and it'll make me thinner.
No.
Yes.
Good try. Good try.
I already tried it.
So you can sort of see, if you pull it out and put it in different places, you get different designs going on and different colors that are coming up and down depending on which color is coloring it.
Drinking dish soap.
Okay. Now, play with it for a minute, then I'd like you to get your notes out, and I'd like to have a calculator out. Go ahead and put the food coloring back on the back, and if you want to play with your stuff for a while, just let it go. It will go for a while and then quit. When you're done, if you would just rip some out over here in the seats, and then put them in the back, that'd be great.
Can I get more milk?
Having way too much fun, huh?
I'm making
Yeah,
mosaic.
probably.
And there are more toothpicks back there, so you can try putting 2 toothpicks in if you'd like, or 3 toothpicks. I wouldn't, probably should, but
I'm such a child.
you ever had soap in your mouth at all? So- Okay. We stopped on this problem that I'm going to put up right now. Let me go all right. One thing I did do for you, I started looking at what we have left to cover, and I pushed the test out by 1 day. So it is now Wednesday. Okay, instead of Monday. We do have today after school on Thursday the tutoring from 2:30 to 3:30 here in my room. I'm still planning on you coming. I am going to have available for you
That's today.
the review that I've done looking at the new test. So you have the old review at the end of this packet that you've got right now. Here's the new review that has to do with the new test. I've gone and looked at every problem and made one similar for it. So that you have a question to look at. Okay. So I'm planning on hopefully going through you all the answers to this
So on top
on
of my
Monday.
me being like
So again, this gives you a chance to do it by yourself or to come in tonight and get help on the ones you don't know how to do. Okay. Here we go. We are in notes and we're on this problem that we stopped on last time. The gas laws, as far as the gas laws go in this test, I would write them down on my card and I would have them labeled. And so when I start labeling things out of a problem that she's got on the computer, then I can really quickly identify what problem I need to use. Okay, so looking at this one, it says the temperature in C, okay, so I'm looking for T1, of nitrogen sample gas that has a volume of
Is that in the new review?
T1. Nope, I'm not doing anything on the review right now, I'm still just doing notes. Okay, and a pressure, there's my pressure, P1, contains this many moles. Well, whenever they give me moles, what equation am I going to do?
Avogadro.
Curve nerd. Okay, so first thing I'm going to write down with curve nerd is my R. And I do that so that I can remember what my units are. Okay, I want to make sure I'm using the right units. So then I go to T1, and that's my question mark, and it's just going to be T. I put T1 when I was doing it because I didn't know what equation I was using yet. So it's just T. I don't know what it is, but when I solve for it, it will be in Kelvin. And they want me to convert it to degrees Celsius. So if I put that into where I'm writing stuff down, that helps me remember what I need to do. The next thing was volume, 2.50 liters. And liters is in my R, so I'm okay. Then they had pressure, which was 300.4. So if I look up here, I need to be in atmospheres. So quickly I can convert 760 torr in 1 atmosphere. Torr will cancel, and I'll be less than 1, so it'll be 0 point something. Somebody throw that through for me. Say it loud.
0.395.
Thank you. And that's
876532871.
You only need 3 sig figs. Good try, love. Okay, and then it says it contains mole, N is equal to 0.100 moles. All right, now I look and say, okay, I'm looking for temperature, which is right here. So if I solve for temperature, and this is the way I do it, if you want to put them all in first, that's okay. Is it going to be equal to PV divided by NR? Plug in. Pressure is 0.395 times volume, which is 2.50, that was atmospheres, this is liters, divided by mole, 0.100 mole, times R, which is 0.0821 atmospheres times liters divided by mole.
What's the N?
That's Kelvin. N is moles. Okay? So if I look at this, moles cancels right here, atmospheres cancels right here, liters cancels right here. 1 over K is K. Remember when I put it in my calculator, I'm going to go divide, parentheses, that whole bottom is in parentheses. And this just becomes my times. So let's go ahead and throw that in your calculator and get Kelvin. And I do want you practicing this, see if you can do it, because this is the biggest problem. This kid's not doing it. And so when you get to the actual test, you're like, oh yeah, we set that up, and then you put it in the calculator wrong. Okay, so make sure you're trying this.
120.28.
120.28, we'll just go there, okay. How do I get from Kelvin to Celsius? Subtract. I'm going to subtract 273.15 to get to degrees Celsius? Yes.
I got 1,202.8.
Okay, who else got 120? We got two 120s. Did anybody get 1,000? Okay, take your decimals off. Okay. All right, what do we get for Celsius? We just subtract them.
Wait.
1, 2, 3.
I got
153. And since we have three significant figures going down, 153 is enough. We're done. Okay, any questions with anything I did here? I just plugged basically and shut. Would be 155.
I got 152.
Like how much?
I had two that had 152. Okay, so 152, 153, 155. 152.8, so 153. Is that right?
I thought it was.
I used the exact number the calculator gave me, so it's probably just not.
That's okay. That's okay.
It's a
So she probably won't give you one that's so close that you won't be able to say, oh yeah, that's it. Yes. Because we subtracted 273 to get to Celsius. Okay, anybody have problems with this or don't understand what stuff I did every time?
So it would be best to have conversions and equations on the first.
Yes, like I told you, I would put all the conversions if it were me for all the pressures. I would have that list of this is equal to this is equal to this, and then the equations, okay? All right, let's do another one. I want you to see if you can do this. Well, I'll do this one with you. It's a little bit harder, okay? So here we have a 2-gram sample. Well, we haven't had anything that has grams in it, so I'm not sure what to do with that. The only thing that possibly it could go to is mole. So I'm just going to put mole question mark there. Because if I take grams divided by molecular weight, I can get mole, right? All right, so a sample, yes, has a volume. I know what to do with that. That's V1 at STP. Okay, what is my temperature and what is my pressure? What's the temperature? Standard temperature. 0 Celsius, so I want to put it in Kelvin always, so 273.15, great. What would be my pressure? 1, good. 1 atmosphere. All right, calculate the molecular weight. Okay, so I know that mole is equal to grams divided by molecular weight. So if I solve for mole, then I can use the grams to solve for molecular weight. So this is a 2-part problem. Okay, and identify it as this, this, or this. So I know it has to be one of those. So okay, I've got volume, temperature, pressure. I'm going to use Pertner because I can solve for N. And then once I solve for N, which is moles, I can use this equation right here to solve for molecular weight. Are we okay with that? All right, so coming over here, I'm going to rewrite real quickly. Pressure, we got there. Volume's the only thing that's missing, 1.12 liters. I'm going to put P down here so I can just see. All right, so solving for N. N is equal to PV divided by RT. Plugging in 1 atmosphere times 1.12 liters divided by R, which is 0.0821, and I didn't write it there, but hopefully we remember what R is. Atmospheres, liters, divided by mole, times Kelvin. Again, I would write that constant on my card, so I had it. Times by T, which is 273.15 Kelvin. Okay, plugging through. Remember when you do this, divide. This is a time symbol here, and the parentheses stay. Okay. What do we get for N? Plug it through, try it. Make sure you can do it. Borrow a calculator if you need to. Get used to it so you can do it on the test. Okay, what'd you get?
0.0499.
Okay, I heard several that got it. Is there anyone that got something different? Okay, now I'm going to take that, what I had up there, and I'm going to solve it for molecular weight, because I'm trying to find molecular weight. So molecular weight is going to be grams divided by mole. Everybody okay with that rearrangement?
Yes. I got 3,726.28.
So you're doing something different. Do this with me. So 1 times 1.12, which is 1.12. Then you divide, and then put your parentheses around it. And then times through, and then close parentheses.
So N that we just found, is that the molecular weight or is that the mole?
That's the mole. So now we're going to use this equation to find molecular weight. You know mole is equal to grams divided by molecular weight. So I just rearranged it. Times both sides by molecular weight, divided both sides by mole. Okay? Now we're going to plug in what we got. The grams from up here, 2 grams, divided by mole, which is 0.0499 mole. And grams per mole is molecular weight, so what do we get? What?
A number.
A number, good. What
40.
number would that be?
40.
40. Now, I can just stop right there. Which one of these has a molecular weight of about 40? Argon.
Oh, just kidding.
So I've got it. Okay, so that's how you would find out what gas you have. All right? Okay, any questions with this one? Okay, moving on. Steel container contains, this one just looking at it makes me go, duh. A steel container contains a mixture of nitrogen, oxygen, and carbon dioxide gases. The total pressure, PT, is equal to this. The pressure exerted by nitrogen, pressure of nitrogen, and oxygen, whoops, let's try that again. Oh, it's 2 different ones. They just did it in thing. 810 torr, and pressure of oxygen, 920 torr, respectively. So we have pressure total, 2100 torr. What is the partial pressure of carbon dioxide? Well, this is the Dahl law, right? So pressure total is equal to all the little pressures added up. We have 3 pressures, right? Okay, so if I add these 2 up, right? If I add those 2 up and subtract it from the pressure total, I've got that, what's left
That'd
over?
be 370.
Okay, so alright, so here we got 0,317, and we take 2100 minus that, and we got 370 torr is equal to the pressure of CO2. We're done. That's the Dahl law. Whenever they say pressure total, I go duh. Okay, real easy. Just remember duh. All right, here's another one. A 250 milliliter sample. Okay, that's a volume. I might need it later. Of oxygen gas is collected by water displacement. Okay, that means I'm going to have to deal with Dahl law. Because if it's collected by water displacement, some of that water is going to go into vapor. As a result, the oxygen is saturated with water vapor. That's what I just said. The partial pressure of the water vapor, so the pressure of the H2O, is 22 torr. So PH2O is 22 torr. Calculate the partial pressure of oxygen, so I'm looking for PO2. If the total pressure, duh, is 720 torr. What do I have to do?
Take 720 and find X.
There you go. Okay, lots of verbiage for one simple subtraction. Okay, so don't let it throw you.
So we're finding the torr of O2.
Yep, that's a torr of O2, that's it. Remember, pressure total is equal to all the little parts added up. We only have 2 parts. Okay, did I use a 250? Extra stuff I didn't need to know. Okay, all right, next one. The mass of bromine molecule is this. So that is my mass of, molecular mass of Br2. The mass of argon molecule is molecular mass of argon. Whenever they start talking masses, whose law?
The first thing.
Grandma's. And grandma's has to do with velocity, right? Compare the ratio. So it's a velocity 1 divided by velocity 2 equals square root, because it's like a rocking chair, okay, molecular mass 2 divided by molecular mass 1. So I've got to go with what they gave me. This is my 1. This is my 2. Okay, first one they gave me is my first one. Second one they gave me is my second. So plugging in, square root of molecular mass 2 is 40U. Molecular mass 1 is 160U. The U's cancel, so I don't need to know it. The zeros cancel. 4 divided by 16 is 1/4, so it's a square root of 1/4. Somebody that has a calculator, tell me what that is. 0? No, because it's square rooted. Don't let him throw it. Don't let him say. There might be a problem that says. How much? 0.5. Okay. So which one's faster?
Wait, I'm confused about looking to figure out what's faster.
So this would be the rate of this one versus the rate of this one.
And what's the molecular mass?
So when you're looking at which one's faster, this is equal to 0.5.
The bottom's faster, right?
No, the top's
But why?
because the rate's 4.
So the rate if it's faster or slow.
So it's a 0.5.
They're usually looking for the ratio, so we're just looking at the ratio. Okay? The mass of argon is much smaller. Smaller molecules move faster. So the rate of number 2, which is a smaller molecule, is a lot faster. Smaller guy's going to move faster than the guy that weighs 500 pounds. Okay? Yes.
So when you're numbering like your volume 1 and volume 2, do you number that with which one you see first?
Usually, I've got to also look at what's in the rest of the problem. So I need to make sure that the volume they gave me is related to the things that are after. Because they might give me something and it said change to, and I've got to worry about it as 2s now.
Okay, so now
Okay.
I go from 1 to 2.
Okay, now, here's the question. Somebody was just asking, well, how do I know which one goes faster? Which molecule will diffuse faster? Helium or neons? Why?
It's tall.
It's smaller molecular mass. So think of those toddlers, they're moving a lot faster than you sometimes. Okay? All right.
So smaller than
Got a
molecular
riddle
mass.
for you. I need 2 helpers.
Haley would love to.
No, I didn't.
Come on up. We need one more. Okay, come on up. I have 2 balloons here. Here's the riddle. If I, right now, the things between them are closed. If I open them and let both sides play with these balloons, which side is going to get bigger? Which side is going to get smaller?
The green one's gonna get smaller.
Okay, I have one that says the green one's going to get smaller. Who thinks the green one's going to get bigger? How many think the pink one's going to get smaller? How many think the pink one's going to get bigger? Okay, I'm going to open it up and let these guys play with us. Play, play, play. Play with the balloon. Squish the balloon. Come on, squish. Come on. Come on.
I want it to pop in my face.
What's happening? Is it easy for you to squish it down? How come it's not easy for you?
She's thick.
Oh. Not around, but like.
Okay. What's happening, guys?
There's
Tell me
more
what's
pressure in
happening.
this one than in that one. So it
Is
was.
there?
No, because the other one's filled with a heavier gas.
They have the same gas in them. So
Both
I
of them are
opened
helium.
the one, but the one is attached here. I've got these closed because I have 2 holes. So the one is open that connects the 2.
There's more stuff in this one, so we can't all flow out like this when it has little, so it doesn't have as much resistance.
Okay. Think about when you're blowing up a balloon. Think about when you're blowing up the balloon. When is it the hardest to blow up a balloon?
When you start.
When you start. That's because the latex is tighter And because it's tighter, it's exerting more pressure on the air that's inside. As it gets bigger, it gets easier and easier. The latex is farther and farther apart. It's harder for it to push the air inside out. Okay? So, as we look at them, we now have two. Thank you for your help. Okay? So, you got to think about what's happening in pressure-wise with the balloon itself. So the balloon has a small, you have to really stretch it and try and get that latex to loosen up so you can blow it up, right? Because if you take a balloon right out of the box and try and blow it, you get bright red cheeks poke out and you still can't get it to go. Okay? So we're going to talk about this a little bit more. All right, so what's happening? You've got pressure on the inside trying to get out, and you've got pressure on the outside going in. If the pressure on the outside doesn't exceed the pressure on the inside going out, the balloon's not going to blow up. Okay? When a balloon's being filled, I've got to put more pressure on the inside to make it go big. When a balloon is filled and tied, the pressure outside and inside are the same. So right now, as these balloons are sitting here, the pressure inside and outside is the same. Okay? When a balloon deflates, the pressure outside is bigger than the pressure inside, so you actually get a deflation going on. Okay? All right, so now we're heading into a different thing. With the intermolecular forces, boiling point and melting point. You need to know the intermolecular forces. There are basically three of them. London dispersion forces. This is like the London fog. We know it's going to be there every day. We know it happens. We know it's there. We don't exactly know exactly why. We sort of think we do, but it happens in all chemicals. Okay? All chemicals have London dispersion forces. It's just that force that's there that holds them together. And nobody really understands, but it's there. Dipole is when I have a slightly positive side of a molecule, slightly negative, and not a full positive and negative. Don't pull apart, but it has a slightly positive, slightly negative, and so they're like in a pill shape. They're attracted to each other, backwards and forwards. So you sort of have, where did I put the, there it is. You sort of have this thing going on, where I have a positive here, negative is attracted to another positive and negative, but they're not full charges. So we put partial charges. That's a lowercase delta.
Are those just polarities?
Those are just polarities. So they're just slightly positive, slightly negative. That's a dipole-dipole interaction. So it's sort of like static. If I rub the balloon on my hair, it's sort of got a little bit of static. It's attracted to me. But if I run too fast, the balloon falls off. Okay? Hydrogen bonding. We're going to go into each of these a little bit more. The hydrogen bonding only works between nitrogen, oxygen, or fluorine, and a hydrogen. So I have to have a hydrogen directly connected to a nitrogen, oxygen, or fluorine in order for hydrogen bonding to occur. And at this point in time, a lot of scientists believe that hydrogen bonding is just as strong as ionic or covalent bonding. But there's also the other part that say, no, it's not. It's sort of an interaction. Well, when you come to biotechnology and DNA and talking about a DNA structure, there's a lot of hydrogen bonding going on between the DNA that holds our whole complex together. And if it wasn't there, our DNA complex would fall apart. So it's pretty strong. Okay, now we're going to talk about how that affects the high or low melting point and boiling point, if it is a solid, liquid, or gas at a given temperature. So, London dispersion forces, this is the first one we're going to talk about. Basically, these are weak interactions. That's like saying, I am a student at Northridge. That doesn't mean I know every student at Northridge, but I have a belonging to Northridge. So every chemical has a belonging to London dispersion forces. Okay, that is something that holds them somewhat together. Okay? This is because you have electrons moving around the outside of an atom. And at one point in time, there might be more electrons on one side than there is on the other. And it causes a momentary dipole, which is then attracted to another atom's momentary dipole. They think that's part of it. This is temporary, weak London dispersion forces. All compounds have it. The larger the molecule, the more electrons I got running around my atom center, the more chance I'm going to have a dipole. Larger chance I have a bigger London dispersion force. Okay? Now, that being said, a couple of years ago I graded an AP question on this that basically the London dispersion force was stronger than a dipole-dipole because of a big molecule versus a small molecule. So London dispersion gets bigger as you go down the table. Okay? All right, next one. So here we have this London dispersion force, and what happens is you've got these electrons that can be any random place in the molecule. And what happens is the more density with the electrons in one region creates a partial charge. So you can see there's more on this side than there is on this side. Okay? So we have a slightly negative charge on this side, a slightly positive charge on this side. On this other one, less density, okay, again, on this side versus this side, you end up with a slight positive. So negative and positive attract each other. So this is what's going on with the London dispersion. And as long as you can see this in your mind, you'll be able to answer the questions that have to do with this. Okay?
Can you explain that one? Like, I'm still a little confused how you figure out whether it's more positive or negative.
So as you're looking at an atom, it has, say, I'm a fluorine. I've got 9 electrons running around my outside. At any one time, 7 of those electrons might be on the one side and only 2 on the other side. That gives the side that has a 7 a slight negative, and the other side a slight positive because there's only 2.
So when we look at this right here on the left-hand side, since there's less electrons, that's why it's more positive.
So over here, this would be a slight positive.
And what does that little like?
It's just, this is just like a lowercase when we do delta. That's a full charge. This is a lowercase delta, so it's a partial charge. Okay? So you just get these momentary partial charges that attract. Yes?
So as the electron densities move around, because I'm sure they do, would that flip the molecule over and over again?
Yep.
The charges would change and the charges
Yep.
would change too, right?
Yep. And so what happens is when one of these flip, it tends to first force the next one to sort of flip too. Because if I have a negative charge over here, the electrons don't want to be by a negative charge, right? So they flip to the other side, leaving only a few strong stalwart on this side. And that means the positive, because remember in here we have the positive charge of the atom, right? So the nucleus is the positive charge. So as these flip to one side, that makes this side more positive. Okay?
That wouldn't be positive also.
So this side over here would be positive, and this side over here would be negative. And so they would be sort of attracted to each other.
So what's the cross on the black part of the?
That's a positive nucleus. So that's where our protons are. Okay? All right, so let's go ahead and go forward here. That's what's called London dispersion. Next step up, a little bit stronger. The molecule itself is set up so it has a positive and negative. A slight positive and negative, not a full positive and negative. So if I look at it, hydrogen likes to give up its electron, usually becomes a positive. Oxygen likes to take 2 to be like a noble gas, so it's slightly negative. At this point, carbon's not letting them take or give anything. They're making them share. So it's a covalent bond. It's not ionic. It's covalent bound. But it has a little bit of positive on this side, negative on this side, because oxygen's a little bit of a stinker and wants to pull it closer to him. Because I really want to be like a noble gas, neon. I'm close. You can give it to me. And hydrogen says, fine, take it. But carbon's in the middle, mediating it. I said, no, you can't have it all the way. You can have some of it. But you can't have all of it. Okay? So we end up with what's called dipole-dipole, where we have a set, slightly positive, slightly negative side, that does not move because the electrons are moving. Okay? It's set. So it's always that way. Okay? Understand this. You okay? Just remember, the ones on closest to the noble gas will have a slight negative. The ones on the right will have a slight positive. And if you remember that, then you'll be able to determine what the molecule looks like. Is it slightly positive, slightly
Wait,
negative?
left is positive?
What?
Left is positive?
Left is positive.
So towards lithium, it's more positive.
Oh, you said closest? Okay, I'm ready.
So closest noble gases will have the slightly negative side.
Oh, yeah.
Remember, carbon's a divider because it can go either way. And then it's usually hydrogen. They'll have the positive side because it's weaker. Okay, then we look at the hydrogen bonding. This is what happens in water. This is why water, in comparison to any other chemical, has a high melting point, high boiling point, high everything, because we have what's called hydrogen bonds. This happens between the oxygen, which is a slight negative, and the hydrogen side, which is a slight positive. It's a set place, but because it's between the most electronegative elements on the chart, which are nitrogen, oxygen, and fluorine, and hydrogen, we get a rather strong bond. Right here, this is called a hydrogen bond. This is what's in our DNA. Okay, between adenine and thymine we get 2, I believe, and between guanine and cytosine we get 3. So there's a bunch of stronger bonds here going on. Now, like I said, some scientists at this time are arguing that this should be called a real full bond. It should be in with ionic and covalent. Others are saying no, it's not. Actually, it's there, but it's more like a spider web rather than a full bond. Okay? But this is the strongest of the bonds that we call intermolecular. Okay, intermolecular forces, also known as IMFs. So you'll see her refer to them sometimes as IMFs. Intermolecular forces. Because you know we don't like to write everything out, right? Except for molecules. Grr. Okay. All right, so here's our thymine and adenine and our cytosine and guanine, and the intermolecular forces that are going there are our hydrogen bonds. So as we look at our base pairs, it's not that these base pairs are actually connected, but they've got these hydrogen bonds that are connecting. Okay? All right. So here is a summary giving you some ideas of each one of them. It would be a good idea to write a few of them down if you're not already in your notes. So to go back over, London forces are relatively weak. All molecules have them. Here's some examples. Dipole-dipole forces, they're in between the London dispersion and hydrogen. Remember on the London dispersion forces, as you go down the column, they get bigger. Okay, these have a molecule that has a set dipole. Set. It doesn't move around like it does in London dispersion forces, because in London dispersion it goes with how the electrons are spaced around the atom. Some examples are these. And hydrogen and water, actually you'll see them in all three because it has all three. Hydrogen bonding also has strong because it is a molecule of OH, NH, or HF bonds. Now, if you notice where they are, nitrogen, oxygen, fluorine, right before neon, so NOF, right at the top row. That helps you remember which ones they are. You can also put it on your periodic table or on your card. You okay to go on? No? Just a minute more? Okay.
Can we go over this after school today?
Yeah, we can go over anything you want after school. Remember that I'm here after school most days. And then before school it's at 6:45 most days, except when it's bad weather like this. I didn't make it till 7 today. Yes.
So are you going to be here after school today for the?
Yep. Friday though, during tutorial, I will not be here because I'm going to a funeral. Okay, so yeah.
Is there gonna be a video on Canvas or
For what?
like this class and then like the review and stuff?
I can video tonight if that's what if it ends up being something we want to video. Okay? All right, going forward. Okay, intermolecular forces, boiling point and melting point. Boiling point is when the temperature at which a liquid is converted to a gas. Melting point, you know, is when a solid goes to a liquid. The stronger the intermolecular forces, the higher the boiling point. The lower the intermolecular forces, the lower the boiling point. That includes melting points. So, increasing strength of intermolecular bonds, you're going to have higher boiling points over here. Melting points and boiling points, you'll see me refer to them that way. Over here they will be lower. Melting points and boiling points.
Higher MP.
Melting point, boiling point. Okay? So just remember, London dispersion forces are the lowest. Then dipole-dipole, then hydrogen. The higher the bonds, because all of them have London dispersion. Some have dipole-dipole, and then there's just a few that have the hydrogen. Okay, melting point and boiling point, higher and lower. All right, we okay to move forward? Okay, do you have a question? Or?
On the test, are we gonna like identify what type of forces they have?
Okay, so here we go. Methane, if I'm just looking at methane, don't look at what's underneath. If I'm looking at methane, I say, okay, what kind of forces does it have? Well, all of them have LDS, London dispersion forces. Okay, LDS. Does this one have a dipole? Can I get a side that's positive and a side that's sort of negative? No, because carbon's in the middle. So it doesn't have dipole, so I stop right there. Okay, so all this has is LDF. Let's look at water. We know it has LDF, right? It does have dipole because I can get a slight negative on this side and a slight positive on this side, right? So it does have dipole.
How do we know where to like split the? Can we ever split it like up and down?
As long as I can take a delta line with one line and split molecule to positive side and negative side. And this one does have hydrogen bonding because it's hydrogen directly connected to oxygen, nitrogen, or fluorine.
So anything with hydrogen automatically qualifies for LDS.
As long as it's directly connected to an oxygen, nitrogen, or fluorine. This one doesn't have it, it has hydrogen, but it's not connected to an oxygen, nitrogen, or fluorine. Okay?
So how do we know what it is from just that?
So now, this only has LDF, right? So I can predict, just looking, not looking at the bottom, just looking at the top, that this is going to have a lower melting point and boiling point. This one's going to have the higher one.
Because how?
Because it has 3 different bonding things. This one only has 1. So the more bonding things it has, or the higher up on the chart it is, the higher bonding. Or melting point.
So why are these in Celsius and not in Kelvin? If we're
So now we're just looking at the temperature they're melting and boiling at. I'm not putting them into my gas laws. I'm just looking at them. Okay? All right, you can see how different it is. Here's just LDL at negative 162, negative 183, compared to 100 and 0. Okay? All right, let's go forward here. Let's look at these. I have more carbons here than I have here, but they're still the same, right? Both of these just have LDFs. Are we okay with that? They don't have dipole because carbons are in the center. They don't have nitrogen, oxygen, or fluorine directly connected to a hydrogen. Yes?
Wait, so how do you know if it's LDF?
Everybody has LDF. So if nothing else, they have LDF. Okay, so what did I tell you about LDF?
They all have that in common.
They all have that in common, and the bigger the molecule, the more chance it's going to be stronger. So as you look at this, this has 1 more carbon and 2 more hydrogens than this, right? So it has a bigger mass. It also has more electrons, and that's the reason we're looking at more electrons. Because as more electrons, it's more polarizable. Because it's more polarizable, the LDFs are stronger. Because the LDFs are stronger, the melting point and boiling point are higher. Okay? Because I have more electrons that I can polarize, okay, it's going to be a stronger bond. Okay? Going forward here, maybe.
Can you go back for a second?
Can't do anything right now, it looks like.
Never mind, you have to go back.
Okay. All right, so going forward, let's talk about the liquid state, vapor pressure. So we know about evaporation. We've known about that for a long time. We know liquid goes to gas. Whoopee. We also should know it took heat to do that, right? We now know that's called endothermic. We have to put heat in for evaporation to occur. In order for condensation to occur, okay, which is going backwards from a gas to a liquid, are we staying with me? Staying with me? Okay. Okay, in order for condensation to occur, it's going to have to get rid of some of that energy. Okay, so it's exothermic. So you should be able to get some of these you've known before, evaporation, condensation. All we're adding to it is endo and exothermic. Okay, so now we're going to talk about vapor pressure.
So evaporation is endothermic and then condensation is exothermic?
Yep.
Okay.
Okay, so vapor pressure is above a liquid. So if I have an enclosed thing like my water bottle here, and I don't open it up for a while, it will equalize. It'll come to the point where whatever's on top of the liquid will stay in a gas. There's only so much that'll go to the gas, and then it'll start coming back and forth. It'll go from liquid to gas, liquid to gas. It'll come to an equilibrium. That point is called where we have a vapor pressure. When we have a pressure of this liquid above the gas. If I increase the temperature, then more of this liquid goes into gas. If more of the liquid goes into gas, then it hits more against the wall. Well, that is increasing the pressure. If I cool it down, then less of them get to stay up here in gas and they fall back down into liquid and less hit the walls. Okay? So that's vapor pressure. When we get to boiling, we have vapor pressure where it equals our atmospheric pressure. At sea level, that's 760. We're a little bit lower than sea level, and our boiling point's about 96.4 on most days. Probably a little lower today because of the low pressure that came in. But when that reaches, that's when we hit boiling. If you do backpacking, you go up to the top of the mountains, and you try and take some noodle-roni with you, or macaroni and cheese, and you don't take extra salt, and you just boil your macaroni and cheese, you'll end up with musharoni and cheese because the noodles don't boil. Don't get hot enough to actually cook. It just sort of mushes them. So they tell you when you're backpacking to take extra salt, put the salt in the water so that it will raise the temperature of the boiling, and then it'll cook. And then you have to rinse it off because otherwise it's too salty. Okay. Doesn't want to move forward. Okay, so here we are again with some different molecules. Now, this is where the intermolecular forces come in, our IMFs. The stronger the IMFs, the lower the vapor pressure. They don't want to go into gas. They want to stay as a liquid. They want to stay as a liquid. So our vapor pressures are lower. So water here, if I let just water go, it has a low vapor pressure. But if I put methane gas or ethanol or something that has a low, weaker intermolecular force, I'm going to have a high vapor pressure because it's wanting to get out. Okay? All right, then we go to the liquid phase. In the liquid phase, we talk about the viscosity. That's the resistance to flow evenly. Okay, that's the resistance to actually flow. Alex, can you stay with us, please? A viscous liquid feels thick, so it's like heavy syrup. Compounds with strong intermolecular forces are more viscous. Okay? Substances with large molecules tend to be more viscous, yes.
So how do they make things viscous? Do they have like a process or like?
So yeah, cornstarch has a lot of molecules in it. Mm-hmm. You can make it stuff thick.
Like a milkshake, because that's thick, but then if you let it melt, it's water.
Right, because you've frozen it, you slowed the molecules down, you brought them down into a slower state. So as it starts to melt, you're putting energy in it, they're starting to expand and become less viscous. Okay? All right. So how many of you have ever tried to float a paper clip or anything on a top of water or a toothpick? Okay? That's because we actually have surface tension on water. Surface tension on water is when you put pressure on a one water molecule, it actually, because they're attached to each other or attracted to each other because of the hydrogen bonding, it forces this pressure to go out on the ones next to it. So if I'm in the center and it's pushing, it's helping all these. It's sort of like stepping on a tramp. Okay? But if you're too heavy, you go through it. So there's a weight limit on how much that the surface tension can hold. Right. And if we try and do like a ballerina and go down on point on the top of the water, it doesn't work. We're too heavy. Okay? But have anybody ever seen a water skeeter? That can actually walk on water. And the reason why is they're light enough and they spread their weight out. Notice how the whole leg there is laid out. So they can distribute their weight. Yes?
Could we do that?
if we had long legs that went out, okay?
So when you push at one point,
So if he had just gone down on the point, he would fall through.
this one's his leg is flat. It's like on the diagram right there. It says that his leg is just reaching out on the one thing.
But it's not. It's flat over it. This one's not showing. It's actually flat across. So it's actually coming across. Okay. Let's keep going here. All right. So viscosity and surface tension. Again, stronger intermolecular forces, higher surface tension. So if you tried to put a skeeter on oil, it wouldn't be. They'd sink because oil doesn't have the intermolecular forces to make that skin. Okay, oil actually lets them just fall through because it only has London dispersion forces. Water has London dispersion, dipole, and hydrogen. Okay, so that's why we can float things on water. Now you said, well, how can I float on water? Didn't you just say that, one of you? Can you do it on an inner tube?
So if we just like attached inner tubes to our arms, we could like float on water.
Yeah. Don't you already? Don't you do that in the summer? Don't you go tubing?
I thought that was because it was filled with air. And not without spread force.
It's just spread out. Okay, you can feel
Wait,
things
is
there.
that why the pool noodle or noodles flow? Because there's not like.
Yeah, the pool noodles flow because it's surface tension. Yes.
But why would it sink in water and not oil? Because oil is lighter than water.
It will sink in oil, but not water. Yeah. The reason why is oil just has like a dispersion forces. There's nothing holding the things together. It's like water has Velcro and they're holding the Velcro together.
Oh, there's
But oil doesn't.
Think of it, oil doesn't.
Oil
And
doesn't.
so you just slip down between.
So is a ship floating in water because of the
Surface tension.
really?
Is that like why when you lay on your back?
So depending on the shape of the boat, do they float better or worse in water?
Isn't it because there's air inside of it?
Somewhat, but not. Most of it is the shape. If you notice, flat boats will float a lot better. That's how they put a lot of weight. They're able to put a lot of weight in, like to move garbage. Yeah. But if it's like this, they can't put as much weight, or it will sink.
So the oil didn't get
It's very low viscosity.
Balance also.
Is that why when you lay on your back you float? Because like
No. Okay. All right.
Balance is a balance.
For some reason, my board just doesn't want to move on today. Okay. You love spiders too. They know how to use this. Okay, we did the surface tension experiment. We actually broke the surface tension when we put the detergent in. So we broke the surface tension, and therefore the molecules were able to move more freely, because now they're not attached or velcroed to the water molecule next to them. Okay? Okay, solids. They can either be crystalline or amorphous. Has anybody heard of amorphous before?
Like changing.
So this one is sort of weird. On amorphous, it actually is a random arrangement. It just sort of goes together however. If it's regular crystalline solid, they make crystals. Make beautiful crystals and go together. Amorphous just sort of go together. There's no rhyme or reason. Okay? Okay, sounds like we need to take a brain break for a minute. Everybody stand up, shake, do whatever you need to. Get up off that thing. Shake it, you feel better. Get up off that thing. Shake it, you feel better. Seriously, stand up. Stand up. Stand up, shake. Move your legs, reach for the ceiling. Shake, shake, shake. Get up off that thing. Shake it, you feel better. Get up off that thing. Come on. Get up off that thing. All right, we got 30 more seconds. Shake it, you'll feel better. Come on, you two, get up. Get up, get up, get up. Get up, get up, get up. Shake it, shake it, shake it. Shake it, shake it. We've actually proven this helps. When you start to actually start to water, get up, shake, do something exercise, and then you can go back. Move your arms. Take a deep breath. I know, it's funny. You think I'm really strange, but it's okay. All right, 15 seconds, coming back down and getting back ready. Here we go. I know this is not information day, but I want to make sure we have Monday so that we can review. Okay, so we can go back over. Because the first time, sometimes it doesn't get in here, right? It might be thrown at you, but it slides off. Okay. Alex, I need you guys to be paying attention, okay? All right, so going forward here, and of course my board doesn't want to be going forward. Okay, so something as example of amorphous is cotton candy. So it just sort of goes together, no rhyme, no reason. Okay, it just comes together. Rubber also does that. So those are examples, yes.
So would amorphous be like a puzzle? Because it just goes together?
But a puzzle has to go together a specific way. You can't just put it together, right? It doesn't just randomly, things just don't stick. This one, cotton candy is amorphous.
Wait, how come it's not crystalline? Cause like,
Well, when you think about like how cotton candy's formed.
It has a, if you don't, she just asked if it has a weak bond. If you look at the crystalline form, they're pretty short bonds between them, right? If you look at amorphous, some are long, some are short.
So
The long ones are weaker.
So for instance, like what a colored pencil be a crystalline solid.
Because it goes together a specific way. Okay? I keep wanting to come back there. Okay, going forward. Okay, another amorphous that you're probably very familiar with is glass. Glass is an amorphous solid. And if you go back, and my daughter does a lot of anthropology work, the older glass, they actually can go and measure, and it moves. It's very thin at the top and very thick at the bottom because glass does move. It's viscous. So over time, it will flow, but it's slow. Okay? Sometimes they're formed when you cool things too quickly. That's one of the ways you can make amorphous solids rather than crystalline. If you want it to form right, you cool it slowly, that you get crystalline. Some examples, like I said here, are glass and rubber, some plastics. Okay, going forward. You also have crystalline solids that are ionic, like salt, NaCl. They go positive, negative, positive, negative, positive, negative, negative, positive, negative, positive. And molecular solids, such as water, when it makes ice, it will line up as a crystalline structure because it has a specific way that it likes to go. Okay, some other crystalline structures are what we call network solids. We can cool glass down so it actually makes an SiO2 bond that is very nice and neat, but if we cool it too fast, we get the amorphous. We can get network solids that make diamonds. We can get metallic crystals like copper and other metals that have seeds of electrons. Metallic solids are basically a lattice of the atom itself, and the electrons move freely. Oh, right there. Got it? Mm-hmm. Okay. One more type of equation. I know, this is a really mix-up chapter 2. So you have your gas laws. Then we talked about phases. Now they're going to talk about specific heat. You got to keep these straight. So gas laws have to be in Kelvin. Specific heat has to be in Celsius. Gas laws Kelvin, specific heat Celsius. This is how much energy do I have to put into a substance to raise it 1 gram of it 1 degree Celsius. Okay, that's a definition of what a specific heat is. How much energy do I have to put in to raise 1 gram 1 degree Celsius? Metals have relatively low specific heats. Water has high. Yes?
You said gas laws, Kelvin.
Gas laws have to have Kelvin. When we get to specific heat, it has to be in Celsius. Okay, so here's how specific heat works. Specific heat is the amount of energy in calories or joules needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. Oh, that has too many calories, right? When we talk about food calories, that's actually lab kilocalories. Okay? So when we're looking at specific heat here, we're looking at the heat divided by the mass times the change in temperature on the bottom. The larger the specific heat, the less the temperature will change. Okay, so as we look at water and we're waiting forever for the water to boil so we make our macaroni and cheese, it seems like it takes forever. That's because water has a high specific heat. It takes a lot of energy to get it to change 1 degree Celsius, okay, compared to everything else. So here are some, I think I put this table in your notes for you. This is some examples of some different substances and how much energy they give off. Okay? Notice this. Water, as a liquid, has 1.0 or 4.18 joules per gram degree Celsius. Nothing else comes even close. The closest one is probably on this chart, propanol, at 2.56.
I'm lost.
Water's right here, 4.18. I'm looking at the second column. Usually we use the joules in lab. Sometimes we use Kelvin. What?
There's just 2 rows.
This is 2 different.
Oh.
Yeah, I'm a bit behind.
Okay, yes.
So how come like water G or water S is different than water L?
Okay,
Well,
so
liquid,
water
gas,
is
and solid.
liquid, gas and solid.
There's like grams.
Okay, we're going to be using this chart a lot. Okay, going forward. So how do we calculate specific heat? How many calories are needed to heat a pot of water with 160 grams of water? From 25 to 100 degrees. So we are in the liquid phase. We haven't changed phases. So we can just use the specific heat of water as 1 calorie per gram degree Celsius. We've got the mass. We've got the change in temperature. So it's going to go through about 100 degree or 75 degrees change. So to find the calories, I just take the mass times the specific heat times the change in temperature, and I've got my calories. Oh, too fast? Okay. Well, people weren't listening, so I was figuring you didn't need to know. Okay, so you just first of all identify everything you have. Okay, identify everything you have. Once you've identified everything you have, find your delta T. Delta T is just the final minus the initial temperature. That'll be 75 degrees. And since they asked for calories, I'd look back on the chart, and the calories for water as a liquid, because between 25 and 100 degrees it would be liquid, is 1 calorie per gram degree Celsius. So then I would plug it into, I like the equation this way, where you go Q, which is also delta H, is equal to MC delta T. And C, I learned it as CP, you learned it as C, however you want to remember it. That's your calories, your specific heat. And you just plug in. So we have a mass of 1,600 grams. We go that times 1.00 calories times the change in temperature is 75. So this is just the step. So identifying it.
So what's C, calories, and then?
It's your specific heat. So it's calories per gram degree Celsius. So we plug into this equation right here. Okay. This is what we do when we would plug in, and we would get this many calories. Now, since there's that many calories, I would probably divide it by 1,000 and get it into kilocalories, which would be about 120 kilocalories or 120 calories, which would be on a cereal box kind of thing that you could solve for. So it's just as another equation I would put on my card. I would also have the specific heat of water in calories and joules for liquid water. Yes.
Go back to the last slide. Is that the equation?
So basically that's what I wrote before. So heat can be expressed as Q or delta H is equal to mass times the change in temperature times specific heat. And I learned it as CP, but sometimes they
So
just
Q equals delta H.
Yep. Okay to go forward? Next page is just plugging the numbers in. Okay, usually we don't write the ones down here because it's just units. I would just put calorie per gram degree Celsius and not put the ones down here. All right, so last thing we need to talk about is energy and phase changes and energy and phase diagrams, because she uses those a lot in on the test also. So remember, melting is endothermic, I have to put energy into it. Freezing is exothermic, I'm taking energy out. That, when I transition between phases, that energy I have to put in or take out is known as something. For freezing to liquid, it's known as heat of fusion. From liquid to gas, it's known as heat of vaporization. Now, that's because the water temperature doesn't change. So at this point, we don't use specific heat. We use heat of fusion times the mass, or heat of vaporization times the mass. We don't use temperature change because it doesn't change. When we times it by 0, it says we don't have any energy we have to put in. But we know we do. You have to put energy in to change phases. Okay? So, how much energy in calories is absorbed by 50 grams of ice cubes melting? The heat of fusion is 79.7 calories per gram. Okay, so what did I just tell you you had to do? Look at the units. Here's your big clue. What do I need to do?
Change it.
No.
Wait, so just do 79.7 times 50 because there's
There you go. That's all you have to do with heat of fusion or heat of vaporization. Look at your units, and all you're doing is timesing it. And that tells you the calories it takes to melt or to vaporize something. Or when you condense it, how much energy is given off when it condenses. Or how much energy is given off when it freezes. Okay? Real simple and easy. You okay? So all we're doing is using that little conversion factor, and we're just timesing that by, and we get our calories. Okay? These are slides from her, so there's a little extra stuff that I wouldn't usually do in it. Okay? All right. Vaporization, I told you the same thing. Vaporization is just going from liquid to gas or gas to liquid. Same stuff. Okay? So, sublimation to deposition, same thing, I'm changing a phase. They usually don't have you do any of these problems. It's usually vaporization, condensation, or freezing, or melting.
Can you go back? There was stuff you had to write on that slide.
You okay to go forward? No? Writing furiously. We good? Okay. And sublimation and deposition. Most people have heard maybe of sublimation, but deposition probably is not something that you know. Deposition is how they create dry ice. What dry ice does after is sublimation, where it goes from a solid to a gas. Okay, so that's a real life idea that you can put in your head. It skips the liquid phase. Iodine does that a lot too at room temperature.
But is there a liquid phase in it?
There is a liquid phase, but you have to go up higher in pressure or higher in or lower in temperature.
So how can you keep iodine liquid in room temperature?
So at room temperature, you actually want to keep it a little bit low room temperature to have it a solid. So otherwise it goes to get vapor, so you make sure the lid's tight so you don't lose it.
You can use like a cold glass where you condense it.
Okay, so really quickly, you need to know what each phase or which thing is doing each process. If it says melting, you need to know it's a endothermic process where energy is absorbed. If it's freezing, it's exothermic, energy is released. If it's vaporization, it's endothermic because energy is needed. Condensation, exothermic, energy is released. And you need to know the phases of each of them. Most of you have heard most of these: melting, freezing, vaporizing, condensing. It's probably the bottom two that you don't know very well, which is sublimation and deposition. Okay? Just know what they are, what's happening. Is it exo or endothermic? And is energy absorbed or is it being released? You okay? All right, now, that being said, we do have heating curves and cooling curves. Heating curves go up to the right. Cooling curves go down to the right. So, if you're looking here, anytime I reach a flat point on these curves, that is my melting point or my boiling point. Okay, so I can read off what the melting point is and the boiling point. This is the water. So it's very simple. Anytime on the slope here, that's when I'm using my Q equals MCP delta T. Anytime I'm flat, I'm just taking the heat of fusion times the mass, or the heat of vaporization times the mass. Okay? Now, having said that, you can determine how much energy it takes to go from a solid at this temperature to a gas at this temperature. You just have to go Q equals MCP delta T to here, heat of fusion times mass right here, Q equals MCP delta T right here, mass times heat of vaporization here, and Q equals MCP delta T up here. Remember the CP for each of your states was different, right? That's where you go back to your chart, right? Hold on a minute. Okay. We got, I think, another one right after this. Yes, right here. So this is a state. So this is, I think, more what you need to write down here. So this is a heating curve. This is a cooling curve. So they just are backwards from each other. Can you see that? Heating, cooling. Heating, cooling. Okay, but it's still the same thing. The lower the temperature, you're going to be more of a solid. The higher the temperature, you're going to be a gas. It's just backwards from each other. So instead of melting and boiling, I'm condensing and freezing. But you're still using the delta H or delta F there. Okay? One is just up, the other one's down.
Is there anything past gas?
What?
If you heated gas to a certain point.
Just get a super hot heated gas. Okay, so this goes through it again. Basic same thing. Now, the one thing I like about this is it sort of points out right here the heat of vaporization and the heat of fusion. That's how you usually see them. This one sometimes will have FS or US on it, and this will have vape. So you know it's heat of vaporization, heat of fusion. But that's what you use here at this part. So to find Q here, you would go delta H vap times the mass. Here you would go Q is equal to delta H fusion times the mass. Okay? On the angles, and I think I've got it on the next slide, you would use the Q's. Yep. It can be a capital Q or a smaller q. We usually use the small q to do that, but this is your equations that go with each part of the graph. Okay? So anytime you have a slope, your Q equals MC delta T. Anytime you're flat, it's just mass times the vaporization or mass times the fusion.
And you said Q is the same thing as delta H.
Yep, Q is the same thing as delta H.
So what's the difference between like Q2 and Q1?
So Q1 is just heating a solid. Q2 is melting the solid. Q3 is heating the liquid. Q4 is vaporizing the liquid. Q5 is heating the gas. Okay? All right, one last graph. This one is just putting all of them together. This is a Y graph. This is the last one, so we're going to hurry quickly and talk about it. You should be able to read any point on this. So if they gave you a temperature and a pressure, you should be able to say, oh, that's in the liquid area, or that's in the gas area, or that's in the solid area, or that's on this line where condensation vaporization is happening. So on this, and this is often found on ACTs and stuff, this graph and the last one, they want you to read. They want you to be able to read off the graph. And all the ACT is can you read the graph and tell me what it says? Okay? So, be able to read off the graph. Just remember the center of the Y is liquid, and closest to the Y-axis is solid. And you know the X-axis is gas, and everything's great. The critical point there, past that point on pressure and on gas, it doesn't matter how much pressure I put on it, I'm just a gas. Doesn't matter how much pressure I put on, I'm just a gas. I'm too hot, it's too much energy, I can't condense it down anymore. Okay? At the triple point, we can actually boil ice water, given the right pressure. Okay? And then it just goes into your examples. Okay? So I can go back to the other thing, but this is just examples here. Just testing stuff that we've done already. And that was the end. Okay? So look at your review. Look at your review. We'll be going over it more on Monday. Please take care of your stuff. Kids have to do some dishes for the stuff at the back. Sorry for taking the whole time, but we did make it through. There it is.
Haley, are you